All right, so the first type of chi-square distribution or hypothesis testing that we want to do is testing the goodness of fit. So we won't actually do this example, but I'm going to use this as a way to kind of help set up what we're going to be trying to do in this section. So up to this point, when we've talked about hypothesis testing, like we might have compared orange to a color or brown to a color. So here the goal is we're trying to look at a whole breakdown of lots of different colors all at once. So again, when you're thinking about these types of hypothesis tests, these are like kind of multivariable. Lots of different things are going on at the same time. So the idea is if we've got colors of blue, orange, green, red, yellow, and brown, then the number that we have here is what's going to be called our observed. So this is what we noticed when we opened up our bag. And what we might predict is that, on a bag of M&Ms, maybe every color is equally likely to occur, that there should be the same percentage of every one of them. Now, we know from past examples that we've worked on, we know that that's not the case. There's a certain distribution that goes into each one of them. But let's just pretend for a second that all of these are equally likely to occur. Then if we want to figure out what our expected column should look like, then what we could do is take the total number of M&Ms that we actually found and then divide it by the number of colors that there are, then that would be the number of expected M&Ms we would expect to get in a bag. So let me add these together real quick here. So I've got 212 plus 147 plus 103 plus 50 plus 46 plus 42. So it looks like we've got 600 M&Ms total. And so again, since there's 6 color, then what that means is if we take 600 divided by 6, then we'd expect there to be 100 blue, 100 orange, 100 green, 100 red, 100 yellow, and 100 brown. And so in a testing for good fit, that's one of the things that we're trying to do. We're trying to see, does the distribution of the colors match what we would expect the colors to be, or does the whatever that we're interested in match what we would expect to have occur or anything like that. So with this one, without even doing a hypothesis test on it, we can pretty much see that there's definitely some major differences between the observed and expected. In fact, green's the only one that kind of falls along the line of what we might expect if we think each color should be about 100. Otherwise, in some cases, they're ridiculously bigger. In other cases, they're ridiculously smaller. So these two things are going to be how we'll sort of start a lot of our problems to make sure we know what our observed is, what our expected is, and we're going to use these to help us calculate what our chi-squared test would be and what our hypothesis testing will actually look like. All right, so leave this for now. We're going to do another example that's going to go along those same lines, but I wanted to just kind of think about where we're heading with this direction. All right, so when it comes time to calculate our chi-squared test statistic, since we have a lot more data going on, it's definitely a lot trickier, and this is our chi-squared sub t, just to remind you. It's a little bit trickier than just sample mean minus the population mean all divided by the standard deviation. So it ends up being based on that observed and expected columns that we formed up there. And so if you notice, what we're going to do is take our observed column minus our expected column and square each one of them. And the reason we're squaring them is because we want to make sure that all the values are positive. Because if we don't square them, what we're going to end up with is the observed minus expected, all divided by expected, is going to be around 0. So we need to square them all just so we can get a nice test statistic out of it. And then when we divide these by the expected, and then we're going to sum all of them. So remember, this is our big sum sign. So it's a lot of work. It sounds like a lot of work, but I'm going to show you some calculator tricks that we can use that's going to make our life much, much easier, that's going to allow us to find these test statistics in a much, much quicker way. All right, so last thing on here, we've got our observed minus our expected squared. So this is just abbreviations of the same thing that we've got going on from above. And when we're looking at these chi-squared values, since these are all right-tailed tests, the bigger the chi-squared sub t that we get, the more likely it's going to be a reject H naught. The smaller or closer to zero it is, probably the less likely it is that we're going to reject H naught in these cases. All right, so again, just as a reminder, our p-value we talked about last time, we're just going to be using our chi-squared CDF to find our p-value. And our chi-squared sub t is going to be hopefully somewhere to the left of there when we do them. All right, so let's take a look at some of the criteria that we're looking for our testing of goodness of fit. So again, chi-squared testing is all based on degrees of freedom, like t intervals were. So for this one, our degrees of freedom is just going to be our k minus 1, where k is the number of categories that we're looking at. So not the number of things total. So if we look back at the original question, we had 6 colors. So each of those colors represented a category. So in that case, our degrees of freedom for that M&M one would have been 5. So 6 minus 1. All right, so our hypotheses, so again, this is another nice thing about hypothesis testing with chi-squares, is these are always going to be exactly the same, these claims. We don't have to worry about anything any different. So the null hypothesis will always be that the data fits whatever distribution we're assuming. The alternate hypothesis will be that it does not fit. So in this case, the observed frequencies match the expected frequencies, or the observed frequencies do not match the expected frequencies. Or if you wanted to simplify these we could say that O is equal to E, or O is not equal to E. And so even though we're using not equals, this is still a one-tailed test because of a chi-squared, but this is a nice shorthand if you don't want to write the observed frequencies match the expected frequencies over and over and over, because it's always going to be that exact same claim for every single one of these problems. So O equals E, O not equals E is a little bit quicker and easier to think about. All right, so next thing we have to do is we have to calculate our test statistic, which we talked about above. And so again, I'll show you how to do this on the calculator. So I'll show on calculator. And then just like in the last section, when it comes time to find our chi-squared sub c, our comparison, we're going to have to use the table for that one. So again, because we don't have a nice inverse chi-squared function. So again, these are always going to be right-tailed tests. So when it comes to calculate our p-value, it's always going to be of this form, where our chi-squared test statistic is our lower bound, some ridiculously big number is our upper bound, and then finally our degrees of freedom is the last thing we type in. And then lastly, drawing a conclusion. If p is less than alpha, then we're going to reject the null hypothesis, just like we have before. So this means that the data does not match the expected distribution. Or if p is greater than alpha, we fail to reject the null hypothesis, and there's no evidence that the data doesn't match the expected distribution. So again, remember, it doesn't necessarily say it is true and that it matches. We just don't have sufficient evidence enough to prove that's true. All right, so let's come back at the next video, look at an example so I can give you a chance to look over this and make sure we've got it down. And then we'll go through an example just to see how we set everything up and how it's done. So good luck.